Okay, so this is my presentation of the experiment that we've done over the last 2 weeks in chemistry lab. It was the determination of the density of a set of plastic beads using 2 different methods. And I got a little cheesy with this. It's mind over matter or mass over volume, which would be the equation for determining density. All right, so the premise of this experiment was that the quality control department for a manufacturing firm that makes the plastic pony beads has had a problem, and they're trying to determine if these beads are okay to be distributed. So they've wanted different physical properties of the beads to be assessed, and one of them is density, to make sure that they're the proper composition weight for the amount of space that they take up. And I made a cutesy little joke here about melting point, and maybe that would be more fun to set the beads on fire, but maybe plastic burning wouldn't be the best thing. Apologies for the cat screeching in the background. All right, so given that our group has density, how are we going to assess density of these plastic beads sitting in front of us? All right, so density is defined as the amount of mass an object takes up with reference to how much space it takes up. So mass in an object over the amount of space equals density. So there are 2 ways that we've been assigned to do this. There's one which I tend to think of as the easy way, which is to directly measure the mass of the beads and then measure the volume. Then you get a calculator and divide that mass by the volume. So mass is easy. You just plop your beads on a scale. What about volume? Also, speaking of which, calculator. You remember when they told us in grade school that we weren't going to have a calculator everywhere with us that we went? Phones are awesome. All right, so this is the displacement method. I like to think of it as when you're at, kind of like algebra, you're adding 2 plus 3 equals 5, and then, so say 2 is your mass, and then x is your volume, and then 5 is your end. So 2 plus x equals your end volume. So first you mass the beads, that one's easy. Then you start with a measured volume of water. It recommended to start with around 20 mils in a graduated cylinder. And then you add the beads after you've already taken their mass. And then you reassess the volume afterwards. So when you subtract the end volume of water plus beads minus just the volume of the water, then that's how you end up with the volume of the beads. The calculation's pretty easy from there. Subtract mass divided by volume is the density of the beads. And it doesn't matter how many beads that you've put into this equation, the weight per the volume figures it out, so it's just the density of a single bead. All right, so then the different method by which to determine density is that of flotation. So this concept takes into consideration the theory of neutral buoyancy. And this is when an object is of the same density as a solution, it will float in the middle of the solution. So what we essentially did was take some glycerin, plop a bead in, and add water, and then you kind of monkey around adding a little water, little of glycerin until the bead floats in the middle. The idea is to mix it thoroughly in between so you end up with a homogeneous mixture. So it sounds great in theory. In practice, it got a little touchy, and this one kind of gave me fits because I was being a little bit of a perfectionist about it. But, so, here's what we ended up with. So on the left is trial 1, and you can see it's just about, maybe 44 mils, and the bead is about 21. So again, I was being a perfectionist, and I don't know, maybe it's a little more than 44, maybe it's like 45. Again, I don't think the bead is exactly in the middle. And then you can pretty clearly see on trial 2 here, it's probably about 10, 20, about 28, and then the bead is much higher up than the exact middle. So again, I had a hard time trying to get it in the exact middle because it was really touchy. You could add a drop here of glycerin, a drop here of water, and it would rocket the bead either to the bottom or the top, and it was just really hard to attain that perfect balance. And of course, I'm being a perfectionist about it. So, all right, so here's the data for the first trial, which is displacement. So we only had 3 data sets because someone didn't turn theirs in, and that's fine. So the takeaways from this are the data range for our group was a little wide, to be precise. I think what really threw it off was my data. And if you look here, the numbers of beads I used varied pretty wildly, and everyone else kind of stayed within 3 to 4 beads of each other. I went all the way down to 8 and up to 27, and I think that's what threw mine off a little more, because you can see that those are the ones that were a little bit wide. So it gave us a range that was a little wide, so it's almost 0.06. And then the group average for density was 1.030 grams per milliliter. And then in comparison to, this is the flotation data, and we had all 4 participants this one. All right, so group data. You can see the range is a lot smaller here. It's 0.016, but the density is still pretty close to what it was for displacement. So displacement was 1.030. This is 1.032 grams per milliliter. So we'll get to that later. So back to analysis for the displacement. Again, this was the simplest to perform. It kind of seemed the most direct measurement to me, because you really were kind of measuring the volume as directly as you could. The mass was easy to do, and then you calculated from there. Possible sources of error: you could not dry the beads not appropriately entirely in between trials, so you might have some residual water left on the beads in between trials. That would increase the volume of the beads. Also, I think, especially this is where I ran into a little bit of variation with my answers, is that you could use different numbers of beads for each trial, and I think given that the beads aren't all the exact same bead, this could cause some variation in your answer. Alright, now on to the analysis for the flotation. Alright, as previously stated, it was a pain to achieve that neutral buoyancy, and then a very small addition one way or the other could change it pretty wildly. I also had trouble mixing for homogeneity, so the glycerin and the water didn't go together very well, and reaching down in that long graduated cylinder with that rod was kind of hard to scrape all that sort of viscous glycerin up from the bottom. So I had trouble making sure it was really, really homogeneous. Also, this only assesses 1 bead at a time, so you're just getting a look at 1 bead, whereas the other experiment, you have many beads involved. However, this data was pretty tightly clustered. The range was pretty small at 0.016. This does indicate a better precision. However, there's no way to really evaluate the accuracy of these two, because we don't have the true value of the density of a bead, so the accuracy is unknown for both of these. Alright, so wrapping it up. The statistic shows flotation should be more precise. However, we weren't given a true density for what a plastic bead consists of. However, displacement for the both of them was pretty similar. Displacement was 1.030 grams per milliliter for displacement, and the density for flotation was 1.032 grams per milliliter. Not a huge difference there. Alright, so some of the sources for error, I already referenced drying equipment between trials, the sample size, so whereas flotation only had 1 bead, displacement had several. The volumes for flotation, so you could either start with a tiny amount of glycerin and put your bead in and then put your water in, or you could start with a whole ton of glycerin and then kind of chase it back from there. I think that would contribute to error, because the smaller the sample size you have, the more room there is for error. And when I say sample size there, I mean the amount of glycerin. So I think to make the flotation method a little bit easier and a little bit more simple to monitor in terms of if you're getting a good even mix, I think that you could probably color the water, or color the water and the glycerin, just to try to use that as a barometer of if you're getting it mixed accurately. Alright, which is better? So the accuracy, we couldn't assess. The precision, sorry, Pippa. Sorry, there's a dog here too. So flotation did show that there was more precise data garnered from there. However, I preferred displacement. I feel like there was a lot less room for error. So, okay. That's my presentation. Any questions? Thanks.